Greetings. I decided to do Chapter 20, Section 2, Number 4. Coming into this lesson students should have an understanding of basic rigid motion, dilation, specifically that dilation preserves the shape and the angle of measure, and angle relationships. We're given in Part A the two triangles in the top left-hand side of the screen. And right away I would ask students if there was a way that we can use basic rigid motions to map the smaller triangle onto the larger triangle such that the 89-degree angles can coincide and the 48-degree angles can be in similar positions or corresponding positions using their knowledge of angle relationship and basic rigid motions. And they should come up with an image on the right which can better demonstrate the relationship between the known and the unknown measures. From there, they can use their understanding of the formula for dilation to find the scale factor K. This also clearly demonstrates that the two sides created by the largest angle are provided, so we can use that relationship to determine our constant K. Students should also know when using a smaller segment to determine the size of a larger segment, we're going to use multiplication, which is what we did in step 3. And to use a larger side to find the measure of a smaller side, we're going to use division, which is what we did in step 2. And hopefully they come away recognizing that relationship. Next, we're given this image in B. This one's a little tricky because the line segment to create the second triangle doesn't go to the vertex of the big triangle, so that can throw them off a little bit. But once they deconstruct the image and sketch the two triangles independent of each other, they should be able to better understand what we're doing. Again, we're given the measure of the side opposite the largest angle for both triangles, and we can again use that relationship to find our scale factor L, which then again we can use to find the lengths of measure of the two missing sides. In C, we're given these two right triangles. Again, hopefully students deconstruct the image and then use their knowledge of basic rigid motion such that the 90-degree angles coincide. Also, they'll be able to use their understanding of angle relationships and vertical angles to determine that these two angles are equal, so we can place them in corresponding positions. And once we do this, we again can use our understanding of dilation and how it preserves shape and the measure of angles to determine our constant K and then find our two missing sides. Unlike the previous examples, we are not given the angle or both measures of the side opposite the largest angle, but we do have the measure of the two legs down here. And we can still use that to find our constant K, which we can then use to find the measure of our two missing sides. In D, we're asked to find the measure of the height of a tree. Again, we use our understanding of similarity and our understanding of dilation. We know that these two triangles are right triangles, and they share this common angle here. So then, because of that, we can use our understanding of dilation to find the height, which is 30 feet. In E, we were asked to give the ratio of the area of the triangles in part A and C. I'm just going to do it for part A. The ratio of the area of similar triangles is equal to the square of the scale of the scale factor, i.e. K squared. We can use the fact that these triangles are similar is something we proved in part A to demonstrate why this is true, which is what I tried to do on the right hand side of the screen. So we say the larger triangle ABC is similar to the smaller triangle EFG. And based off of what we determined in part A, we know that A over E equals B over F equals C over G equals the height of the large triangle over the height of the smaller triangle equals some scale factor K, where K is some constant. Using that knowledge, we can begin to construct our formula. So we have the area of our larger triangle over the area of our smaller triangle. And we know that F and B share a relationship, i.e. B divided by our scale factor K will give us this length F. So we can plug that in for F. And similarly for H, we know the height of our larger triangle divided by the height, or divided by our scale factor K will give us the height of our smaller triangle. So we substitute in those values, we do some algebra, and we arrive at our answer, which is K squared. Finally, we were asked to determine a way to find the width of a pond, and they told us that we could use our strategy in part D when we measured the height of the tree. So we find one end of the width of the pond and we walk perpendicular to the width, some known distance x. We backtrack some known distance z, and then measure perpendicular from that known distance x, some known distance y. So we create these two 90-degree angles, and then we have this shared angle. And then we use our understanding of similarity and dilation to determine the width of the pond. Thank you for your time.